Now let's talk about retrosynthesis of Diels-Alder products, and as always with retrosynthesis, what we're dealing with is looking at the product and working backwards to the starting material. So let's look at what we have here. Here's a Diels-Alder product. Remember, retro just simply means reverse. So here's a Diels-Alder product. How do we go from this product to the starting material? So let's look at it. So here are my arrows, right? If I start here at this pi bond and I shift this pair of electrons here, that means I'm going to put a pi bond here and break this sigma bond. So the sigma bond that's here in red, I'm shifting those electrons here to make a pi bond, and then the sigma bond here in red, I'm breaking that and shifting those electrons here to make this pi bond. Alright, so here are my two Diels-Alder substrates. Here's my diene, which came again from this pair of electrons coming here and this pair of electrons coming here, and then here's my dienophile, which came from this pair of electrons in this bond coming here to make the pi bond here. Alright, so here are two examples. So let's try this retrosynthesis. And normally, if you're working backwards with a Diels-Alder product, a good strategy would be to start at the existing pi bond and shift it. Okay, so we're going to take this pi bond here and let's put the electrons in. So we're going to, and these red lines indicate where my pi bonds are going to be in my start material. So let's take this pair of electrons and shift it here. So we shift here, take this pair of electrons and this bond and shift them here. So we're going to break this bond and put those electrons here, and then we're going to break this sigma bond and take those electrons and move them here to make a pi bond. Alright, so 10 seconds. Hopefully this is what you got. You can see here, here's this pi bond here is formed when I shifted this pi bond to here. Alright, this pi bond is formed when I use these electrons in this sigma bond to put them here, and then this pi bond in the dienophile comes from me taking this sigma bond and using those electrons, shifting those electrons here in order to make this pi bond. Alright, so here's another one here. Let me put the arrows in. Alright, so you see shift, break, and break. So let's see what you got. 10 seconds. Okay, is this what you got? Hopefully it is. Here again you see I shift this here to make this pi bond. I take this bond and I break it and shift those electrons here to make this pi bond, and then I take this bond, this sigma bond, and I break it and I shift those electrons here to make the pi bond here. So notice I started with an alkyne. Alright, so an alkyne is my dienophile, this is my diene. Alright, so the last thing we want to talk about is sometimes Diels-Alder reactions can result in what we call bicyclic systems. Alright, so if I take a cyclic diene and an acyclic dienophile, then I should get in the product, the mechanism doesn't change, the arrows are still the same, right? I have a pair of electrons coming from this pi bond to here, so that's going to result in the sigma bond here. I have a pair of electrons coming from this pi bond to here, resulting in the sigma bond there, and then this double bond gets shifted over. So let's look at the product. So this is the product. Notice I have a bicyclic system. So here's a 5-membered ring, 1, 2, 3, 4, 5, and then here's a 6-membered ring, 1, 2, 3, 4, 5, 6. So you can see the outline is a 6-member ring, and then within that there's a 5-member ring. So we call that a 5-6 fused ring system. This carbon here is what we call a bridgehead carbon. This is the same carbon that was here in the 5-member ring of the diene. Alright, so if you notice, the carbonyl here is on a wedge. Whenever you form these bicyclic systems, then you have the possibility of forming what you call either the endo or exo product. Exo, if I take this ring and I turn it upward so that you can see it from the side, exo, it simply means that this is my fused bicyclic system, and this area underneath, this vacant area, if I think about this bicyclic system like an umbrella or a house, there's a vacant area underneath it, and there's also area here outside of it. And so the exo product means that whatever this group is going to be outside of the vacant area. Okay, but there's also another product which is here. Right, notice on this product the carbonyl is on a dash line, and because of that we call this product the endo product. Endo meaning inside. Again, this vacant area under here, this little house, it's kind of like the shape of a house. This little area underneath the house, if the substituent is under the house, we call that endo. Alright, so what I want to do now is show you some 3D depiction of these products, because it's kind of weird when we look at these rings and when we draw these fused systems. It can get kind of weird and kind of tricky, and so I want to show this to you in 3D. Here are my 3D models. You can see they're flat like they were drawn, but here is my 5-member ring. You see 1, 2, 3, 4, 5. And then in the yellow, you'll see my 6-member ring. 1, 2, 3, 4, 5, 6. So again, it's a 5-6 fused system. Alright, now let's look at these rings, and let's move it up a bit. And so now you can see in 3D, you can see the little bridgehead carbon kind of poking up here and here. Alright, those are my bridgehead carbons, just like we looked at in the other example. So here's that open area underneath the fused ring system, and here's my carbonyl underneath. And then if you look on this side, the carbonyl is not underneath that fused ring system. So here's the open area, here's the carbonyl out here. And so again, this would be an example of endo, and this would be an example of exo. As always, if you have any questions, you can tweet, you can email, or you can drop by my office. Peace.